So what we need to define then first are a couple terms, so minute ventilation versus alveolar ventilation. And the minute ventilation is defined as the amount of air that we breathe in and out each minute. It's pretty relatively straightforward. So it's our tidal volume times respiratory rate. So average tidal volume is 500 mLs per breath, time 12 breaths per minute, which is our breathing frequency. And so this gives us a minute ventilation of about 6,000 mLs per minute, or in other words, 6 liters per minute is what we're breathing in and breathing out. And the question is does all that air that we breathe in, all of the 6,000 mLs, available for gas exchange? And the answer is no, because what we know is, although we take in 500, the first 350 that goes in makes it into the alveolar airways, but the last 150 mLs is up in the conducting airways. And we talked earlier how the conducting airways, no gas exchange takes place. So that 150 is not available for gas exchange. It's only the 350 that is. So we have to then figure out for alveolar ventilation is to say it's going to be our tidal volume minus the anatomic dead space. In other words, this is the conducting airway dead space times the respiratory rate. So it's 500 minus 150, which is 350 times 12, which gets us to a normal physiological value of about 4,200 mLs per minute of air moving into the alveoli. So an important differentiation: minute ventilation, the total amount of air that moves in; alveolar ventilation, how much of that actually makes it into the alveoli, so subtracting away the conducting airway, or it's also called the anatomic dead space. And so on average, as it turns out, therefore, about 70% of the air that we breathe in is available for gas exchange. And obviously 30% is not. May seem not very efficient, but keep in mind, as we talked about, the conducting airways do perform an important function, or functions. They clean, they warm, and humidify, so they do perform an important function. So what we then want to get a sense of is we have a couple things to consider here with respect to alveolar ventilation. So alveolar ventilation can be influenced by many factors, including the tidal volume, the respiratory rate, medications, exercise, age, altitude, disease. So an important question is, what's more important for ventilation: the depth of the depth of the breath, or the frequency? In other words, the tidal volume or the respiratory rate per se. And so what this table shows here is a way to kind of illustrate this. We're actually going to start with the subject B. So subject B has a tidal volume of 500 mLs and a respiratory rate of 12. So minute ventilation is 6,000. This is exactly the calculation we just did on the previous slide. And what they've done is they said this is minute ventilation. Now they're going to subtract away dead space ventilation. And what they're saying is it's 1,800 mLs is the dead space ventilation. And how they got it is they said it's 150. They know that each breath at the anatomic dead space, or the conducting airway, is 150. And if we took 12 breaths per minute, 150 times 12 gives rise to the 1,800. So what they're saying then is 6,000 minute minus the dead space of 1,800 gives rise to alveolar ventilation of 4,200. And this is exactly the same numbers that we just got through calculating on the previous slide. So if we look at subject A, though, what subject A has done is taken tidal volume, doubled it up to 1,000, and actually halved the breathing frequency. So overall, minute ventilation is still the same. It's 1,000 times 6 is still 6,000. But in this case, when you subtract away the dead space ventilation, it's only 900. And the reason why it's 150 per breath, but there's only 6 breaths per minute. So 150 times 6 is 900. So we now say 6,000 minus 900 gives rise to alveolar ventilation of 5,100 mLs per minute. The bottom line here then is that the take home is that by essentially doubling the tidal volume, we're getting much greater alveolar ventilation, even in the face of a frequency that's gone down. So we can actually ramp up our tidal volume, double the tidal volume, get significantly better alveolar ventilation, even in the face of decreased breathing frequency. What's shown here in subject C, in this case, this person has dropped tidal volume down to 150 mLs, and the frequency has been ramped up to 40 breaths per minute. And in this case, the minute ventilation is 6,000. And what we have to do, though, is subtract away the dead space. And in this case, the dead space ends up also being 6,000. And the reason why, if you think about it, is so 6,000 minus 6,000 is 0. But if you think about it, if each tidal volume breath is only 150, essentially all that means is what they're doing is ventilating the conducting airways. That by the time, just as the air gets right to the end of the conducting airways, it's being blown back out. So essentially there would be no alveolar ventilation. So what this shows is, although if it's a relatively small tidal volume, but with a very high frequency, you get an alveolar ventilation. So at the end of the day, what is the most important thing to understand is it's really the depth of the tidal volume that determines alveolar gas composition. It's not necessarily a high frequency is not going to do it in the face of a low tidal volume. So it's the depth of the tidal volume. Therefore, it is more important than respiratory frequency per se. And so this is really the physiological basis for why things such as yoga, breathing that's done during yoga, or perhaps during labor and delivery, has physiological relevance. So that breathing is very specific, it's very defined. It might be a specific deep breath. And again, there is a physiological basis for those things working because, again, ultimately what's being altered in this case is the tidal volume. But again, the takeaway from here is that really it's the tidal volume that sets up alveolar gas composition. And again, what we have to have is a very good and deep and sufficient tidal volume. Again, on average, normal about 500 mL per breath is under tidal volume conditions, or in tidal volume breathing. So what we want to start to think about now then is getting into these partial pressures. And so we're going to switch gears a little bit and talk about Dalton's law. So the partial pressure of a gas mixture is the sum of the individual pressures, and this is Dalton's law. So at sea level, total pressure is 760 millimeters of mercury. So this is 1 atmosphere. At sea level, 760. And for the sake of argument, we're going to say that here in Gainesville, we're at sea level. And oxygen is the composition of the air that's in the atmosphere. Oxygen is about 21%. In other words, if it's 760 at sea level, 21% of that is about 160. Nitrogen is about 79% of the gas composition, so it's about 600 millimeters of mercury. CO2 and water really in trace amounts, very, very low. And again, obviously the majority is nitrogen and oxygen is what exists in our atmosphere. And again, what Dalton's law says is the total, which is 760, has to be the sum of the individuals, which is 160 and 600 is going to be the total. And so what becomes important is we move from the atmosphere to the tissues, the pressure of oxygen is going to drop in a stepwise manner. So we just went through the calculations. Here's the partial pressure of oxygen in millimeters of mercury. In the atmosphere, it's 160, and again, we calculate that as being 21% of 760. And then as we get into the delivery, bringing it into the lungs, it drops down, alveolar gas, arterial blood. So there's a stepwise fashion that it continues to decrease as it goes on its physiological path. And specifically what we're going to focus on is the pressure from the atmosphere to the venous blood. So this is really going to be the main area that we're going to emphasize. So what's shown on this slide then is a few, there's really some numbers shown here that basically just committing to root memory. I think this is also kind of they're explained here in this figure, but then here's the calculation. So there's really, kind of three different ways to get at the same number, the root memorization, kind of a flow chart to it, as well as a calculation, but essentially it's the same number. So where we're going to start out at is here on this graph. And so we're going to start in atmospheric air. And what this shows is the partial pressure of oxygen is 160 millimeters of mercury. And again, the question is, how do we derive that? So what's shown here is atmospheric partial pressure is 760 times the FiO2. This is the fraction of inspired oxygen and the fraction of inhaled, which is 21%. So 760 times 21% is 160 millimeters of mercury. So again, the number here in the box is 160. How we derive that is through this equation. So again, what we need to commit to memory, atmospheric oxygen is 160 millimeters of mercury. So it starts in the atmosphere, and then it moves into the lungs, and as it passes through the conducting airways, it's clean, warm, and humidified, with humidified being the operative word. And by the time it reaches the end of the conducting airways, the pressure is down to 150 millimeters of mercury. And what Dalton's law says is, again, the pi at sea level is going to be 760. And if something comes into the picture, something else will have to be reduced. And so clearly what we see is the stepwise fashion where oxygen is now gone from 160 to 150. And in this case, what's gotten bigger now is the water. The water was relatively small at 5.7. It's now up at 47. So not quite, but almost a tenfold increase in the partial pressure of water in this case. And so if the water got bigger, and that has to be a reason as to why we would expect to see the oxygen dropping. So again, the pi is only 760, so as the water comes in, the oxygen has to be reduced to some extent. And how we calculate that is to calculate the inspired partial pressure of oxygen. So it's 760 minus 47, and this is the water. So the 47 is the water vapor pressure. And what this is the in millimeters of mercury. So at 100% relative humidity, at 37 degrees C, water exerts 47 millimeters of mercury. So we say 760 minus 47 is 713, and now we multiply 713 times 21%. And what we now get is 150 millimeters of mercury. So we started at 160, we dropped down to 150. So again, just commit the memory, atmospheric is 160, inspired is 150. And now the question is when we get down here to the alveoli, what we see is oxygen has dropped down to 100 millimeters of mercury. And being at 100 millimeters of mercury, again, if it went from 150 now down to 100, the question is what got bigger? And the answer is it's the CO2. The CO2 is almost negligible here, really was negligible in the inspired, but is now 40 millimeters of mercury is the pressure that it's exerting. So it's exerting a fair amount of pressure. And that is what's now displacing the oxygen and bringing it down, because again, Dalton's law says that the total has to be the sum of the individual gases. And so to be able to calculate this, then this 100 number, we use the alveolar gas equation. And what it says is it's P inspired O2 minus alveolar CO2 over R, where R is a constant, which is 0.8, and we'll come back to this in a minute. So our P inspired is 150, and this is what we just calculated up here. This is the same 150 that the P inspired, minus alveolar CO2, which is 40, over 0.8, so it's 150 minus 50, and this is 100 millimeters of mercury. So again, we said 160, 150, and eventually down to 100. This is how they're calculated: 160, 150, and then again 100. And again, committing the memory, the important numbers you have to understand is the partial pressure in the atmosphere is 160, inspired is 150, and alveolar is going to be 100. So now we're at 100 millimeters of mercury in the alveoli. And so we want to know then, as we move from the lungs and the oxygen moves into the blood, it's going to basically, we're going to have gas exchange occur in the capillary network, and then it's going to head back to the heart. And coming out of the left heart, essentially in the arterial blood system, that the partial pressure of oxygen is going to be about 100 millimeters of mercury. And an important thing to look at or to consider is from the right heart, as we talked about in the first lecture, that we know 100% of cardiac output goes to the lungs. And so all the blood, all the venous return blood is available for gas exchange. But as it turns out, a very small percent of the blood will go through the capillary network and never come in contact with ventilated alveoli. So this is said to be blunted shunted. It's a physiological shunt, generally estimated to be about 1%. In this figure, they had it, I think, a little high at about 5%. And so what you would expect to see is the oxygen in arterial blood, the partial pressure is usually about 99, but clinically most people just simply see 100 millimeters of mercury. But again, so if you have 100 setting up in the alveoli, you'd expect almost close to that setting up in the arterial blood. But again, keep in mind, under normal conditions, even under very normal conditions, we always have a small amount of physiological shunt going on. And so generally, you'd expect your arterial to be slightly, just a hair less than what you're going to have in the alveoli due to, again, this blood that never comes in contact with ventilated alveoli. So in the arterial blood, the partial pressure of oxygen is 100, CO2 is 40. It goes out to the tissues. And what's shown down here in the tissues is it says 40 minus for oxygen. That means the oxygen went from 100, and if there was a decrease, it was a minus, so it dropped down to 40. The CO2 is 46 with a plus. That means it had increased, so it went from 40 to 46. And then basically we'll come back around this way to head back up to through the venous return to head back up to the right heart and end up going through the right heart to go back again for gas exchange. So the important thing, again, to take away from this is it becomes very critical to understand the partial pressure of oxygen in the atmosphere, in inspired air, and ultimately in alveolar air. And the alveolar gas equation becomes very important because it's used as a diagnostic tool to determine if someone is to be able to use as a differential diagnostic tool to identify what might be the cause of a disease. Because if someone is sitting in an office, if they're sitting at sea level, and you know that the composition of atmospheric air is 21%, you should be able to make a pretty good prediction of what their arterial gas composition is. And if you measure that, if it's measured in clinic, and it's not that, then clearly something's wrong. And so this is a good indicator and predictor of what something should be. And if it's not that, then clearly someone would have a disease. So what becomes important next is to go through and use the alveolar gas equation as a means for calculation of understanding what we can calculate for partial pressure of oxygen and figuring out when it's going to be sufficient and when it's not going to be sufficient. And again, what you need to do here to commit to memory in atmospheric, again, 160, 150, 100. Those are again the step down from 160, 150 to 100. And then again, we always have to know that the normal arterial oxygen, a P little AO2, is also going to be about 100, and then arterial CO2, P little a CO2 would be about 40 or so. So again, these have to be committed to memory. And so what we can talk about, though, is what happens when, in looking at this equation, we really have two variables in the alveolar gas equation. It's going to be the barometric pressure and the FiO2. So now we're going to start going through scenarios where those can change a little bit and kind of understand what might happen as we start to change some of those variables. So what happens if we simply change breathing in Gainesville as opposed to room air, which has 21% oxygen? What happens if we switch to 100% oxygen? So barometric, so simply breathing 100% oxygen in Gainesville. How we translate this is the FiO2 is now 100% instead of 21%. And since it's Gainesville, it's still going to be 760 as the barometric pressure. So first thing we want to do is calculate P inspired O2. So it's 760 minus 47 times the FiO2. And 47 is the vapor pressure of water. Water is always 47. And again, it's simply the vapor pressure that's exerted when water is 100% relative humidity and 37 degrees C. So it's always 47. So we now have to say 760 minus 47 is 713 times, now in this case, 100%, which is 713. So this is our P inspired O2 is 713. To figure out what arterial oxygen should be, we take our P inspired O2. We're going to plug this into the alveolar gas equation, again, which is P inspired O2 minus alveolar CO2 over R. So it's 713 minus 40 over 0.8, which is 713 minus 50, which equals 663 millimeters of mercury. So what this means then is if you're breathing through a mask device, 100% oxygen in Gainesville, this alveolar gas equation tells us that the partial pressure of oxygen in the alveoli should be about 663 millimeters of mercury. And from this, your arterial blood value of oxygen should be pretty close to that, maybe about 660 millimeters of mercury, again, accounting for a small amount of shunt, but it should be very, very close to this. So they should not be hugely different. And again, if the patient is put on this amount, you'd expect to see, that type of response would be a predictive indication. If for some reason it doesn't change or get up near this value, that would be suggestive, again, of some type of disease going on in this person. So again, it indicates that overall using the alveolar gas equation can tell us and predict again what these values would be. So therefore, putting someone on 100% O2 in Gainesville increases the PaO2 from 100 to 663. And this is a significant increase. Can certainly help someone who's hypoxemic and kind of get them ultimately where they need to be. So the summary of the key points, at least for this, is understanding the difference in minute ventilation and alveolar ventilation, being able to understand, again, the concept why tidal volume determines arterial blood gas values and not the respiratory rate per se, understanding Dalton's law, and again, being able to manipulate and use the alveolar gas equation as a diagnostic tool for determining at least if oxygenation is sufficient in this case.